that you can't take the square root of a negative number. Lots of times in Algebra 1 we'll tell you that because you can't take the square root of a negative number and get a real number answer. So we can do it though, we just have to expand our world from the set of real numbers to add the set of imaginary numbers. And what that's going to look like, an imaginary number means that it can't be put on a number line. It's not something you can actually draw on a number line. Alright? So if you think about it, this is our number system. That all the different sets of numbers that we start with. When we're really, really, really little and we're learning to count, it has to be things we can pick up and hold. 1, 2, 3, 4. These are our natural or our counting numbers. We expand just a little bit, but it's really huge, from natural numbers to whole numbers. And whole numbers, literally, the only difference is you include the concept of zero. That's very abstract, and so for little kids, that's hard to understand. Then as we get older and our understanding expands, we add in integers, which happens to be positive and negative whole numbers. We introduce the concept of what it is to be missing something, a negative number. And finally, we add in our rational numbers, which are simply anything that can be written as a fraction. It can be a decimal that terminates, or a fraction, or a decimal that repeats. All right. Then we expand a little bit more and we add to that, these are all rational numbers. So we add our irrational numbers, and that's simply those fractions that, or things that can't be written as a fraction, which would be a decimal that doesn't repeat or doesn't terminate. The most famous one you probably know is pi. We estimate that to be 3.14, but obviously it's much larger. It goes on forever. Square root of anything that's not a perfect square is also irrational. We simply estimate it to be a decimal value so that we can utilize that. Another irrational number that we'll expand on later is e. And then we add in those imaginary numbers. Imaginary numbers are the square root of negative numbers, right? And we'll use an I to represent those. When we let those two coincide, because they can, we wind up with a complex number, which is both a real piece and an imaginary piece. All right, so we'll start out with, what is the square root of -1? Its value is I. That's where we get imaginary. So we use a letter I for that. And then we want to go ahead and expand, write our various powers of I. So we're going to have, anytime we see I, we think square root of -1, and that is just an I. Well, if I have I squared, that's the square root of -1 being squared. Anytime you square something, it cancels the radical, so that is just a -1. Right? It's not a variable, so I don't have to worry about absolute value. When I look at I to the third, well, that's the same thing as I squared times I. We just said that I squared was going to be -1, so this would be -1 times I, or -I. For I to the fourth, we're going to go back and we're going to say, well, that's I squared times I squared. And we know that I squared is -1, and that's another -1. Negative times negative gives you a +1. So that I to the fourth gives you a 1. Then we go to I to the fifth. Well, let's use that fourth because that's a nice easy one. So we'll do I to the fourth times I, which means it will become I to the fourth is 1 times I is just I. Then we'll do I to the 6th is going to be, how about I to the 4th times I squared? I to the 4th we know is 1. I to the 2nd is a negative 1. 1 times negative 1 is negative 1. Then we can do I to the 7th. Well, how about we let that be I to the 3rd times I to the 4th? 3 and 4 make 7. I to the 3rd is going to be negative I to the 4th is a positive 1, which winds up giving you a negative I as that value. And lastly, for our purposes here, we're going to do I to the 4th times I to the 4th, because 4 plus 4 makes 8. And I to the 4th is a 1, times another 1 is 1. What we're hoping to see, that you'll recognize, is that there's a pattern here. We go I, negative 1, negative I, 1. I, negative 1, negative I, 1. Every 4 imaginary numbers repeats. So if you just learn the pattern I, negative 1, negative I, 1, then just know that that repeats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so forth. So one thing that we're going to ask you to do, if you'll skip to section B, is we're going to ask you to evaluate each of these. So I to the 3rd, we've already established a value there. We know, let's run through. I to the 1st, I to the 2nd, I to the 3rd, I to the 4th. We know that this is I, negative 1, negative I, and positive 1. So for I to the 3rd, we just know that value. It's negative I. First 4 you have to know. For I to the 6th, I could simply sit here 1, 2, 3, 4, 5, 6 and get that this is a negative 1. Something so small that's perfectly reasonable. I to the 9th, I could do that as well. 4, 5, 6, 7, 8, 9. So I know that it's going to be an I. However, as these numbers get bigger, we might want to think about that a little differently. If you'll break that exponent down into multiples of 4, we know 4, 8, 8's 1 before 9. So really this is I to the 8th, multiple of 4, times I, and I just simply look up this value, which happens to be I. Another way of doing it is long division. Since it's a cycle of 4, we can divide 4 into its exponent. 4 goes into 9 2 times. We really don't care how many times. It's this remainder that we're interested. So you get a remainder of 1. That tells you to go to I to the 1st. One way of doing it. I to the 25th, again, think of multiples of 4. We get 24 is a multiple of 4 times 1 more to get to 25. So again, I'm going to get I as my final evaluation. I could do 4 into 24. 6 times 4 is 24. And that remainder is 1. For 242, I might know multiples that go that high. Right off the top of my head, I'm not going to venture to go there. But I can divide 4 into 242. 4 goes into 24 6 times evenly. We bring down the 2. And 2 is too small for 4 to divide into it. So this is my remainder. Remainder of 2, so I'm looking at I to the 2nd, which gives me a negative 1. Alright? The next thing that we'll do with that is we'll actually simplify negative roots. So if you'll slide back to examples. A, we know when we see a negative underneath the radical, the first thing you want to do is think, oh, that's a negative 1 times whatever to get the negative 9. Oh, well, that's a 9. Now you're just going to simplify. We know this value is equivalent to an I. We also know that root 9 happens to be 3, so this simplifies to be 3I. When you run into something like 12, the same concept applies. We'll do negative 1 times root negative 1 times root 12, but 12 will also simplify in its own right, so that would be root 4 times root 3. I know this happens to be a 2. This is my I. and the root 3 just stays. So our simplified version is 2i root 3. You also might run into a complex number where you've got a real number piece without a negative root or an I with it, and then something that has a negative root or an I. You simply want to simplify the root. So we're thinking root -1 times root 81. Oh, 81's perfect square. So that's 9i and a 5. 5 plus 9i. It's customary to put the real part in front and the imaginary part at the end when you're making a complex number. Those can't combine because they're not like terms. If you would go on to the above C, we're going to talk about different operations with complex number. And by operations, what we're talking about is adding, subtracting, multiplying, and dividing. And you can apply the same operations, adding, subtracting, multiplying, dividing, on complex numbers that you can on real numbers. So the things you know how to do, adding numbers, you do that with complex numbers as well. And what that looks like, we're just going to do adding and subtracting today. But if you add, this is telling me to add, my real numbers add, 5 plus 2 of course is 7, and my imaginary parts add. And that winds up being 13i, a positive 13i. So my answer when I add this complex number to this complex number gives me this complex number. When you're subtracting, the same thing applies, but since it's subtracting, it's a good idea to go ahead and distribute that so you don't mess up the signs, especially on the second part. So we'll get a -3 and a -2i. And I'm going to combine my positive 7 and my 4i with that. When I put the real parts together, I get a 4. When I put the imaginary parts together, I get a positive 2i. There's my answer. Works the same even if there's fractions in the problem. So when I put, this one is subtraction as well. So that'll be -6 plus 3i. When I put the real parts together, that winds up being a positive 1/2 minus 6. It's just a fraction, don't panic. You literally could just go ahead and say, oh, that's a -5.5. But if you need to, if it's something that you can't do in your head, you might want to find a common denominator. So we'll make 2 be our common denominator. This becomes 12 over 2 that I'm subtracting from 1 over 2. So that would be a -11/2, which reduces to 5.5. Put your imaginary parts together, the positive 3i with the positive 4i, and we get a positive 7i. Last, this one hasn't been converted to imaginary numbers, so the first thing I want to do is change that to be root -1 times root 9, which will give me 3i. And this would be root -1 times root 16, which would be 4i. And then this one was negative. That's a -3 with it. I'm adding those. And this is 5 plus the 3i. Put your real parts together. 5 minus 2 is 2. Put your imaginary parts together. 3i minus 4i is a -1i. Just like anything else, it wouldn't be a terror if you wrote the 1 in there, but it's an understood one if you don't. Thanks. The last page of your notes has some problems for you to try, if you would, and those answers will be posted on Canvas.